Okay, good to see you all here. So moving forward from yesterday, when we talked about AI applications in lung diseases, let's take a broader view of where the field is going. And let's look at one specific aspect called digital twins. Now, sometimes I wonder whether this was the original digital twin. Some of you will recognize this. It's part of this, it's a mock-up of the main shuttle, where Houston, we have a problem, has become famous in movies thereon. As you all know, there was an oxygen cylinder explosion, a shuttle out of control, people in there, 20,000 miles away, all kinds of alarms going off, and they couldn't make sense of what was happening. So what do? You have a complete mock-up of the same system lying with you. You play till you figure out what those alarms, those combinations could be meaning, and what could be done to rectify the system. Now, of course, this is a sense of not really a digital twin, but a physical twin somewhere else where you keep on simulating. You get a few minutes of radio contact from time to time. In that, you pass on the information. You try to rescue the situation, and it's good. This one worked. So what's a real digital twin? That, I guess, historically would be one of the closest examples we might find. I'm sure there are better ones. The key difference is that you must be updating a digital representation of a physical asset in real time. For purposes that you have chosen beforehand, that digital twin should be acted on to give you results identical to or comparable to what would happen if you did the same thing in the physical world. And this basic idea can be extended from anything. I mean, for example, you could be looking at a jet engine. You could be looking at a car. You could be looking at a manufacturing process. You could be looking at a city. You could be looking at the entire earth. It entirely depends on the purpose, the granularity. A perfect twin, of course, is never possible. But for whatever purpose it is that you want to create the twin for, it should be possible, subject to reality. So what you want is a continuous link, and the Internet of Things today makes it possible. Now, if you were to think as two parts of a digital twin, one is a cyber-physical system. The cyber-physical system is basically measuring all the time. So there have to be some kinds of sensors or descriptors or even a video recording of an athlete when they're doing things. And there must be a way of updating the twin that exists in cyber-physical space. Then there must be principles which are called closed loop optimization. The two must continuously feed between each other, or process controls to monitor, diagnose, predict disease, optimize treatment, whatever it is that you really want to do. Now let's take one of the most useful small things that are not, we don't think of them as digital twins, but they're becoming widely used. Insulin pumps, continuously measuring your glucose, continuously titrating your insulin to maintain a model of what is desired of your glycemic status in the body is actually a digital twin. You have said, I don't want to know about the person. Only thing I'm interested is a twin of their blood glycemia, which now exists. The sensors are there. There's a process control loop, because you can modulate it by giving insulin. You got parameters. I want it between here and here. And continuously on a real-time basis, the two update each other. A classical closed loop system learns what to do, and it's non-trivial. So right after a meal, for a given sugar, a certain trajectory, the amount of insulin you would need would be entirely different from exactly the same value of blood sugar at a different point in the day with a falling trajectory. It's not just the value. So, 180 blood sugar falling from 200 is extremely different from 180 blood sugar rising from 160. And what you would do in terms of giving insulin has to be learned. So now, even if you were to look at applications of AI in healthcare, you're already starting to see smart insulin pumps, which have learned from a large amount of the data. In fact, the very smart ones would learn from your own data because each person is different. So when you have done this in a few iterations, in theory, in a smart insulin pump, you have your own digital twin for your glycemia, for your disease. We don't think of these small things as, a digital to an example, but they are. Let's take ventilators. So when I was a critical care fellow, managing ventilators, you had these ventilator settings in which you give a fixed amount of volume to the person who cannot breathe, who has a tube in. And these are called continuous mandatory ventilation. Then there were other types of ventilator settings where you sense when a person wants to take a breath, and then you put a pressure to assist them. So these were called synchronized ventilation systems. Then there were hybrid systems. But eventually, what was the point? The point was you should be able to measure the amount of air going into the lungs of a patient. You should be able to titrate it to desired levels of oxygen, CO2, ventilation. You must be aware that overexpanding the lung, which is ultimately damageable and fragile, particularly in sick people. Healthy people are actually very tolerant. You don't get into an ICU on a ventilator until there is some problem. And pushing a lot of air can create rupture of the lung. So you have to maintain the pressures. So you have to work with a variety of constraints. Today's generation of ventilators are increasingly becoming capable of understanding the parameters. And as you force air in, you can also simultaneously measure the pressure that is being generated. You can maintain a track not only of the volume, but the volume history. You can decide that periodically I need to ventilate this person high, then I can let the lungs rest. So you can not only do something that is instantaneous, but takes into account the entire ventilatory history over the entire day. In theory, this will go over even longer times. So ventilators are becoming complicated. Not the mechanics of the ventilator, they remain exactly the same. But thinking about the ventilator as a way of obtaining data about the lung and thinking about closed loop optimization as what is it that you're trying to do with the ventilator can allow a person who's not a critical care specialist to theoretically outperform. Sometimes, in fact, I wonder if there will be a time when a critical care specialist who tries to use their own brain in trying to do something might actually do more harm. There's a very interesting paper by a medical doctor who served in the ICUs, then decided to go become a computer scientist and came back, in which they tried to model the most important thing we do in ICUs other than ventilate people, which is maintain their blood pressure. To be very honest, as a critical care doctor, if you can keep a person's heart beating, blood going to the organs and oxygen levels good, 90% of your job is done. Once in a while, if the kidneys have failed or something else, you call that specialist to come manage that particular organ. But this is 90% of what we do. So when blood pressure falls, what are the two things one can do? One thing one can do is give volume. You put more volume into the blood system, pressure will rise. The other thing you can do is to make the vessel constrict. When the vessel constricts, for the same movement, the pressure will rise. And this, in a very loose thing, is about 80% of pressure management. One thing is called a pressor to raise pressures. One thing is called volume. So what they did is they trained an AI system on the data of hundreds of patients in an ICU and asked the AI system to come up with strategies for maintaining blood pressure. The AI system was actually better than the average doctor. The typical finding was the average doctor reacts too late, too hard. When the BP first starts falling, humans have this wonderful quality called hope. So you hope it's a blip. It's going to go away. You don't react. And then it falls further. Now you react with pressors and fluid and everything very hard. What they found was the AI system was more gentle. It reacted earlier and gave small incremental decisions. Because it has time, it has all the time in the world. A doctor will come see in a fixed intervals, make a decision, then not plan something that requires them to again check in 5 minutes and do something again. It's an advantage that an AI system has. So I understand why doctors behave, why they do, because I've also been a tired fellow, with 50 patients to take care of and making these decisions at some point in my life. The other great area is pacemakers. Your heart does not have only 2 or 3 set rates. it behaves differently based on the different loads coming onto it. Again, higher quality pacemakers based on other electrical parameters it is seeing can be dynamic. They can respond to demand, and they can give you a far better quality of life compared to a static rate pacemaker. Again, great amount of AI work goes into these, and these are all actually examples of little digital twins. Cars are also getting there. So the Porsche Taycan, and I hope that somebody in this room either has one now or will have one in the future, their entire suspension has a digital twin. Why? Because your car needs servicing. You can say 5,000 kilometers, 6 months, 3 months. But how is, 5,000 kilometers on the roads of, I don't know, London, comparable to 5,000 kilometers on the road of Gurgaon? I have no idea what Bengaluru roads are like, but I hear they're not great either. But the point is, if you are trying to say the car needs servicing because it incurs certain amount of loosening and damage, it can't be based on kilometers, it can't be based on time. It has to be based on driving style, road quality, jerks, everything else that comes. So the Taycan actually comes with a digital twin for the suspension, which will tell you when it is time for the car to get serviced. Already you're seeing things like TPMs, right? Tire pressure monitors. They're coming in even the low-end cars. So you know when it is time to fill your air. You don't go every 2 weeks, I will go and get my air checked. Now the TPM tells you when you will do it. So your TPM is a little digital twin of the air pressure of your tires. Similarly, you can have it for your suspension. And of course, I do wonder, one day in Gurgaon, a car will roll out, go over a massive speed break or a speed bump, and as it rolls out of the showroom, it'll come time for servicing again. So, these things will also occur, I'm very sure. But here is a more serious example that is really very important. Jet engines. They are amongst the most important things for safety. You don't want your aircraft to crash. At the same time, the aircraft is so expensive. Taking it for servicing routinely actually is worth a huge amount of money to the airlines. And again, the need of an engine that flies over the Arctic, or flies through the sandstorms in Arabia, or flies simply over nice and clean South India, are entirely different things. So an ideal GE jet engine, which actually comes with a digital twin, should have sensors for the quality of the air that is coming, environments. And of course, Arctic doesn't really matter because at the altitude they fly, it's anyway very, very cold all the time. But still, there are other challenges that come depending on the routes that you track. So GE already builds all these things into its engine. In fact, GE not only does that, GE has an entire division for digital twin creation. GE recognizes that you may want a digital twin to be made for any very valuable physical asset. If you reach out to them, they would be happy to work and see what can be done to create a digital twin. And of course, in a country like Grenada, that is looking at possible changes in sea levels because of climate change, they are building digital twins of their coastlines, expected rise of water levels, in planning their building for the future. And there is now something called Virtual Singapore, that is the entire city's 3D digital twin. I mean, it doesn't do as much as it sounds like it would. You can pretty much go there and see everything right now. But in theory, they are anticipating a time where a city planner would be able to use the digital twin to do far more than is currently possible. And there already talks about an Earth digital twin, and possibly Gautam knows more about that. From the climate perspective, there are many other things going on. Can we do this in healthcare? And like I said, the first challenge is, what is it that you're trying to model? So you have to understand the level at which you plan to operate. Healthcare is a very big word by itself. And when you take biology, it becomes even bigger. So we are barely at the point where we can even create a real digital twin of a single living cell. Although recently the A549 cell, which is one of the cancerous cell lines, recently an entire ionic channel digital twin was made. But basically, biological systems are far too complex and far too poorly understood. Both are important, right? To be fully represented digitally, genome upwards. But specific organ functions like a machine, particularly at the level of physiology, are more representable. I'm a physiologist, so I'm biased, but physiology is an optimal meeting point of machine learning systems and actually functional parts of the body. Because this is the level at which we really care about it. We don't actually care about our genome. We care a lot regarding our body functioning the way it is supposed to. We don't even care about the biochemistry, to be honest. We don't care our sugar is 126. We care about the fact our nerves should be healthy 10 years down. So physiology is a nice meeting point, which is measurable, quantifiable, almost always relevant to health in some way. If not to disease, then to fitness. And in many things can offer you clues regarding what to do next. So all those planning to run machine learning for health and disease, I encourage you all to have careers in physiology. That's my plug. So let's take cardiology. Now, cardiologists would hate to hear this, but they possibly operate with the simplest organ in the body. It's ultimately electrical and mechanical. We understand mechanics well. If that was the only challenge in building an artificial heart, we would have done it quite nicely by now. We actually do. We have these non-pumping digital artificial hearts. The other part is electrical. We understand that also. So we understand how the electromechanical coupling occurs. We understand the propagation of the electrical waves. We can easily create physico-mechanical models of the functioning of a heart, and because of very complex systems that we have already learned to implant in the heart, we also know how to get data. So we can get data regarding the electrical movements in the heart. We can get data about the mechanical performance of the heart. And these are the only two parameters that really matter for functioning. So we can create nice digital twins. So let me give you an example. So this is kind of complicated, so just bear with me on this. Let's say your heart is very big. Your heart is very big and your electrical wave takes time to travel from different parts. You're at risk for arrhythmias. Sometimes what needs to be done is something called resynchronization therapies, where you actually plot that you will create channels by electrophysiologists in the EP people in the heart space so that these arrhythmias do not occur. And this typically occurs in people with vastly enlarged hearts with electrical problems. And this is done to optimize mechanical functions so this larger heart beats in a more organized way. Problem is, if you get it wrong and the person gets a fatal arrhythmia, they die. But if you had a digital twin and you could be reasonably certain, with at least even 90% confidence, let's say, that intervention that you make on the digital heart, the twin, will reflect what would happen in the real world, you could afford to kill your patients 100 times over in the digital space, find the idea that is most likely to work, then actually touch the real heart. And it's happening. This is the kind of technology we're already at. Only a few places in Germany dedicated to this are currently doing it. But very soon, we will see more and more of this occurring. But there are larger models here. One part, of course, is the usual deduction-induction cycle, where you have mechanistic models and you have statistical models. The reason it works well in the heart does not work well elsewhere. You will hear 100 different models being made by people for digital twins. The reason it works well in the heart is because mechanistically we understand the little bit that I said about the heart. When you don't understand and you're relying entirely on data science and AI to help you build the model, the likelihood of crashing and burning is far higher. So your ability to look at the model and understand it because you understand the system, then pick the right one is invaluable even today in medicine. If you have to pick a problem, don't pick a problem that is more statistical, less mechanistic. Pick something where both sides are at least balanced. Gene expression studies type models typically are here, not so much here. So again, warning for all the genomics lovers, it's very good, but for actual medical decision making, you really want these two sides to be balanced. Simply saying it works in a statistical model does not translate well into actual healthcare if time is important to you. In time, it might. And this is, of course, the resynchronization therapy, cardiac resynchronization therapy that I told you, and there's a big difference between the two. Now comes a larger problem. The larger problem is, let's say we want to make a model suitable to the next patient that comes in, but all the data that we have is only from a few patients. And we know every patient is different. How do we solve this problem? because the next patient that comes in will come from the general population, while all the data that you have is from previous patients that you have. So all these ideas of digital twins must include patient-specific digital twin, and you can do this in a way that was advanced by saying, given all possible sets of patients you have seen in the past, who is the closest match to the patient you are seeing today? That problem in itself is a very nice computational problem, to the extent that in Stanford, there was a person, Vibhu Agrawal, who's currently now with us at Ashoka, did his PhD on the topic that if you get a new patient coming in and you're going, oh my God, what does this patient have? I have no idea. You can search through the entire database of Stanford to find a previous patient that was like that and get a printout the next day. It's a paid service. It's called the virtual consult, with a printout of such patients, what happened to them, what they responded to, and you can sometimes use that to change the entire direction of management. So Nigam Shah leads this work at Stanford, and this has now been taken up by Mayo Clinic as well, and we are still figuring out how this can be expanded to India, because clearly patient presentations in India could be very unique compared to what it is abroad. But we need sufficient data for it. It's not quite there. So what you want is patient data, population data, augmentation of the two, and sometimes a mechanistic understanding allows you to generalize beyond simply matching patients. So population level data, when combined with individual patient data with an idea towards mechanistic understanding, allows you to create models that would be effective for a new patient that has never been seen before, and there is no perfect match to them. These problems will occur and somebody has to think about. I would love to say that we have done a great job about creating digital twins in lungs, but we haven't. I would like to say it is because the lungs are a fundamentally much more complicated organ than the heart. Perhaps they are. But there was an effort during the pandemic, the Breathe Easy effort, Project Breathe Easy, when people were trying to see how can we optimize the use of ventilators and maximize the benefit to people. As with many things during the pandemic, it has died out, but it made good progress in the time it was there in optimizing ventilation, figuring out which patient would respond better, worse, where is it more important. Today, again, we have an excess of ventilators. So idea of who would benefit from ventilation and how is no longer as important right now, but the lungs do work. And I would, like I said, the ventilator to me is the best digital twin. One limitation with the lung is how do you image it well? You can't do it simply through the normal physiology. And people have come up with electrical impedance tomographies, EITs, which allow you to see ventilation in different zones of the lung and create a simulated image. So the closest we have got is have a ventilator, have EID on bedside, see where the ventilation is going, change ventilator parameters, make sure that optimal ventilation occurs, but still it's not really in practice yet. At the level of pigs, we have done reasonably okay, not so much beyond that. Another way of imagining digital twins is in cancer. But again, to think of this, ask what's the question in the mind of the doctor and the patient. One question is, what is this patient going to respond to? Can I create a digital twin that tells me the response? The next question could be, well, all cancers have a finite non-zero risk of recurrences. Can I create a digital twin that is looking at re-emergence of cancer? Can I see the spread of the cancer where I don't have it under control and maybe partial responses to certain efforts, including radiotherapies? And of course, how all this is changing in response to the various treatments that are being given. So this is a very, very high value area. I think probably more effort is going into creating cancer digital twins than any other field. Most success is there in the heart. Most effort is there over here. So already we have genomic versions of what the cancer would respond to. For some of them, we have clear mechanistic understanding that allows us to do this. We have figured out how to measure cell-free DNA in the blood. We have started doing what is called exosome sequencing, very small little particles released by cells containing a bunch of things. We can actually sequence them. So a recurrence of cancer can be found from liquid biopsies. We call them liquid biopsies because you're using the blood as a biopsy tissue. Serial engineering has got better and better. So particularly with PET scans. You guys probably don't know what PET scans necessarily are. So one of the things about tumors is they have a high glucose utilizing metabolic activity. So if you create a labeled glucose that can be detected on imaging and you inject it into the body and you think of high utilization as a hotspot, you will end up with an image that shows hotspots all over the body. And then of course there's anatomic imaging with MRIs, etc., that shows you some kind of a difference in tissues or their densities. And again, the same problem comes. You will have individual data, but to generalize to the next patient, you need population data. So the same types of efforts, and the more mechanistic you can make it, the easier this problem becomes. So there's always going to be a strong need for good, high quality biologic investigations to help convert statistical models into things that you actually understand. This is another area where a huge amount of money comes in, which is drug discovery in pharma. Now, this actually has multiple levels. One level of a digital twin in pharma is simply about the manufacturing process. It's about the plant itself. I'm not talking about those, but those are actually also quite valuable. The manufacturing process can be simulated, so you don't even start manufacturing until you know that everything will probably go right. What is more important to me in digital twins in drug discovery and pharma is the idea of evidence itself. Now, classically, and this is a loose interpretation of the word digital twin, but so you're kind of simulating a lot of things. Classically, we use RCTs. Now, any of you who have ever participated in RCT know the speed at which things occur. So if you end up in a field where new drug development is occurring at a pace faster than old drug trials, then you are in a quagmire. How do you move forward? By the time you get to the end of trial of this one and you're looking at it to publish, three more things have come. So one idea, and please don't get me wrong, randomized controlled trials remain the highest level of evidence in medicine. Nothing that I say should detract from that, but given practical considerations, that A, they're expensive, not everybody wants to fund an RCT for an old drug that is cheap. There must be a way of generating evidence from the real world, which is not based on an RCT. So you have to essentially create populations and population simulations and mixing, dense data acquired on tests and spare data that is coming from routine healthcare. And sometimes it works really well. And one example I can think of, that they were thinking of an NIH-funded trial for a drug or a rare disease. It would have taken years to do because it's a rare disease, finding the patients, enrolling them, taking consent, and then doing things. But the drug was a commonly used drug that's pretty much available over the counter. So a person who runs a website called People Like Me or Patients Like Me, that allows people of a certain disease community to come together and form a community. He simply shortcutted the entire trial by going to his community that already had a size greater than the NIH trial would have done, asking them how many of you have tried this drug before, because it's something that you would come across in life, taken it for long period for some other disease. Did you see any benefit to your own disease, other disease? Within the span of a few months, there was community evidence generation. And the short answer was, no, it's not going to work. Not based on experience of actual patients. So you could create, and this all happened it's a real world, but it's all occurring online. So if you were to think about communities in the real world and their representations of their experiences in the online world, you could start thinking of the possibilities of digital twins in that space. It's not a one-to-one representation. It's not like, the original examples I gave you, but it is within the domain of how our imagination can allow us to use these things better. Few really interesting things. I was talking about this to a person who is a sports medicine. And he mentioned some of the highest earning athletes in the world come to London to his clinic. Why? Because by putting a huge number of sensors. Let's imagine it's Roger Federer. I don't know whether Federer is one of his clients, and you're looking at a particular forehand stroke of his. And you're creating an AR, VR simulation in which he's almost playing. And because of all the sensors, you can see whether even a 1 degree or 5 degree change has come from his previous motion. And if you think that's going to create new stress on the joint, so you have those models running, you could tell him to modify that stroke and optimize, get back to what worked for him. So you could do it as a coach, you could do it as a doctor, you could do it for a variety of reasons. So whether it is fitness, and you could do a lot of these things at a cheaper level for people who may not have his ability to pay by simply doing video recordings and then analyzing the video recordings. In football, they have smart footballs now. So they have a bunch of sensors. So when you kick the ball, it sees where it was kicked, the amount of RPMs and curves were put on it. And for a top level footballer, you could create a digital twin of the kick. And if he is worth enough, that digital twin of the kick is also worth quite a bit. So how to maintain it, optimize it, everything is possible, depends on imagination. This is where I'm going to start ending by giving you an example of things I don't think will work that well right now, but are very important to do nevertheless. Digital twins for immunology. What they're proposing to do is to identify the purpose of the digital twin. That's very important. If you don't know the purpose of what you're creating the twin for, it is meaningless. Then you have to, most importantly, create a list of all required components of the immune system. I can tell you from here to here is going to be trouble. It's much less trivial than it sounds. For a given purpose, to know all relevant components of the immune system is actually far more complicated than it sounds. So when I see this plan, I know here they will run into trouble. Because I wish for anything that I think I have some expertise in, I knew this. But the general rule of medicine is half of what you know is false, and you don't know which half. So with that humility in place, I think this is something that is going to give them trouble. But there would be some simpler application that we do already fully understand. And one could then choose a very specific thing over here for which we know 90% of what is required. I don't think we ever know more than 90% on anything. We periodically get shocked and then go downwards. So those of you who participate in these projects, look at the line 1 to 2 quite carefully. Especially on the biologist medical side, you might want to be aware. We sometimes know less than we probably do about that problem. Digital twins for public health, I'm hoping Gautam has either already spoken to you or will speak to you about this. I can't answer a single question on it, but I knew he would be in the room. So any questions that you want to ask on this, I will redirect on that direction. I'm going to end by speaking about a few very important challenges for people enthusiastic about data science and application to health. The first is can is not the same as should, right? Understand why you're doing something. All models have errors. Not everything is actionable. When you use data, you must protect when you do data science, you must be aware, you must protect individual agency. Here I speak for doctors. The idea that data science will absolutely force doctors to act in a particular way is not going to occur. There are privacy issues and there's inequity in data. I'm going to speak a bit more on this. One of the important things for people who think of AI health as a partnership is to never forget who's the senior partner. AI health, AI cannot be the senior partner. Health is always the senior partner because the goals are this. When you look at the work done by DeepMind and how they've gamified things, and now you can do protein folding very nicely. But then you look at developments of DeepMinds towards medical applications, you remember it's not a game. Also winning strategies, for example, that occurred in the Watson, in the game of Jeopardy, may include simply saying, I don't know, go see somebody else. But at a doctor, there's a limit to the hierarchy where you can say, I don't know what to do, go see somebody else. At some point, you have to advise. And that's one of the reasons why IBM Watson did not do as well in cancer as it did in the game of Jeopardy, because it's not a game. And you need a sense of data solidarity. I'll speak a bit more about that in the second talk I give. And this is the other reality. As you start thinking of all these things about digital transformation, applications to healthcare, remember that you will also deal with this as much as this. So this part of India is only at the level of digitization. At best, you will get conventional healthcare paper records that at most you can digitize. There is nothing greater than that. This part of India will give you digitalization, where data is generated from the instrument in a digital format that is usable. The nice thing about doing all this in India is you are at the cusp of digital transformation, where various parts of the ecosystem talk to each other. It's a very challenging area, but India is better equipped to do this than many other LMICs, and which is also why there's a great interest in many people who want to test these ideas in India. Because in theory, your payment systems, your ID systems, your insurance systems are all getting cross-linked. So your ability to get data might get better with time. And if this gets replaced by the true vision of the ABDM, with the wellness clinics functioning seamlessly, and I'm not saying it will occur immediately, but the vision is that you should have, in place of this, something digital occurring at the lowest level. Things could change, but I would say I wouldn't hold my breath on it. Here are the ending points. Unbiased collection of biased data does not make it unbiased. Really important to realize. And I'll give you a very solid example of this soon. As I spoke to you about lung disease, activation maps can tell you where AI is looking. If you don't have activation maps, I gave you an example yesterday where a pneumothorax was being diagnosed by chest tubes. Because all people in a hospital who have a pneumothorax have a chest tube before we do anything else. Patients sent for COVID determination, AIs are looking at the name of the hospital. All these kinds of things occur. But even if you have activation maps, you can only see where the AI is looking, not what it is seeing. So explainability is not complete, even with activation maps. This is an example I'm going to end with, and I think it's really important. So I'll give you a bit of background to it. Who is your biggest friend in healthcare? An insurer who plans to pay. An insurer who does not plan to pay, of course, is your biggest enemy. But the person who has the greatest interest in your health is an insurer who plans to pay for your healthcare needs. So knowing this, in America, insurance companies came out with an algorithm that was supposed to predict who is going to get sicker, but is not yet very sick now. The idea was, by giving them additional care, if you can keep them out of the hospital, you will save a massive amount of money. But I mean, I would go for it, right? I mean, if it keeps me out of the hospital, even if it saves them a massive amount of money, it makes me healthier. These algorithms were used by insurance companies across America. Now, one day, partly by serendipity for some work, Obermeyer was the junior investigator. U Chicago is the senior partners over here. I'm forgetting the name right now. They were arranging by ethnicity the outputs of this algorithm. And this is what they found. On the x-axis, you have the risk score being given by the algorithm. On the y-axis, you have the number of active medical conditions the person has. The dark colored are blacks, the yellowish color are whites, and there is a difference. So to get, let's say, a score of 50 from the algorithm, you have to have more medical problems if you are black. And it keeps diverging. Why is that? Did somebody program the algorithm to be racist? Very unlikely. Do blacks only become sick when they have more medical problems? Very unlikely. If you think about it, it'll make sense. Anybody wants to take a guess? Anybody who has not heard me speak before who wants to take a guess? Absolutely. Poor people go to the hospital when they are sicker than rich people. So if requiring hospitalization is part of a statistical model, poor people would be thought of by an AI that has no understanding of life and society, that they are that sick before they become sick. This is what occurs. Imagine data like this being used in India. Imagine what you already know about our society and see how challenging this is. Now, this is a problem that a person who understands healthcare would have anticipated when the model was being built. But it is extremely likely that when the sketchy design of the statistical model was provided, nobody thought of it, and then after that, they were not directly engaged. These are the kind of problems that as you build digital twins or anything, and especially as you go towards social scale implications, beyond simple mechanistic understanding of organs, you need to be very, very careful about. So I thought I would end with this example because to me, it is one of the things I always think about whenever, big projects come in front of me. So with that, this is a very nice book by Chandrasekharan, the head of the Tata Group, about the digital nation. Technology is not a solution by itself. You really need to think more analog when it comes to healthcare. Thank you for your attention. I recognize that some of it may or may not have made sense. Thanks.
Thanks, Anurag. Questions?
Yes.
Always. So my question is about the explainable side of things and digital twins. So if you were to do this, because my personal opinion is that we are very far away from digital twins for any healthcare situation. So if you were to actually start building a digital twin for something, what would it be? What would your strategy be? That's first part. Because as you showed the last slide, we did something similar, which was published in AAAI for the health inequalities in the US, and how an explainable model revealed some of those things. To be very honest with you, despite having a healthcare background, I did not anticipate everything that was being seen in the model. So it seems to me that it has to be an effort as a consortium, even to solve one small part of this problem. So what could that be, and what would the strategy look like?
Let me take the first example because it also gives me the benefit of the room's wisdom. So an area where I am trying to build a model is to predict COPD exacerbations. And I'll give you the background to why I'm doing it so you will understand the rest of the answer better. COPD is by definition not curable. It's an obstructive lung disease where a lot of your lung is destroyed. Exacerbations occur in patients. So far, the best predictor of an exacerbation is the previous exacerbation, which is simply like saying in English, those who exacerbate, which is not very useful. But it should be possible if a patient is using home monitoring of physiology of the airways to pick up changes that are occurring which are small enough that they would not notice it themselves. And this is the part of the talk I gave you yesterday. This will be easy for you also to get. So you're in a sense creating a small digital twin model of an individual's health. Now, if I had to build this twin for anybody, it won't work. The reason I'm planning to build a digital twin this way is by using them themselves as a self-compensatory background, plus continuous acquisition of their data over periods of time, I would be able to eliminate many other things I do not understand. Then I'm only looking at them changing over time and then from their own self-controlled learning system. So I would keep my ambition small. Now, let's say I didn't want to do this. I wanted something that when a patient comes to a doctor's clinic, without ever having been seen before, I would want to be able to predict exacerbations. Now I need population scale models, right? That's the example I gave you on the heart side. Now for a population scale model, I would need large amounts of data and blood from a large number of people who are routinely presenting. Then I would have to build biomarkers on that and I would get more into the zone of biochemistry. As I said in the beginning, I am less trusting of biochemistry than I am of physiology, because with physiology, we have a mechanical understanding of many things that are occurring. So I would expect such models to be less predictive value. Then I would think about what are the consequences of false positives and negatives. Well, false negatives, I won't worry about so much because earlier I was not detecting them anyway. The best we have right now is those who exacerbate. So let's not worry about false negatives. I would look at false positives. If my false positive rate is 20%, and my real exacerbator rate in a given week is 1% or 2%, I will be sending 10 times as many people to the next care for intervention as I was sending previously. If my false positive rate is 20%, but my real event rate is 10%, I'm sending twice as many. Now, this is getting into the pragmatic side of medicine. If I'm sending for treatment 2 times as more people as I usually send and saving half of them from exacerbating, my medical system will say it is worth it. But if I'm sending 10 times as many people and saving only a few, well, the system will say it is not worth it. This is a financial decision. So while a life is invaluable, so is health, there is a value at the end of the day. So you need to calculate something called number needed to treat, NTT. Number needed to treat is a very simple concept. How many people do you need to intervene to give one person a benefit? It entirely depends upon the false positive rates, the efficacy of intervention rates. If there is nothing you can do about it, NTT is infinite anyway. Any idea what a typical NTT in medicine is? The number of people needed to treat for one person to get a benefit in actual outcomes. Typical numbers of NTT in medicine? We would want it to be 1, right? For every person you treat, they get a benefit. What's a typical NTT in medicine? A 20 itna bhi kharab nahi hai. So, for most things we do around 5 or 6, but a lot of the things that we do close to the numbers you're talking about. And especially as we get to cancers, it is clearly in that domain. So standard, well-tested, regular medicine, more like 5 people you treat, 1 person benefits and outcomes. Aspirin, for example, has a wonderful NTT, but aspirin given to all people you think might have a heart attack, NTT is very, very large. In fact, infinite probably. So recently the trial came on otherwise healthy elderly people that we were giving low dose aspirin to prevent a heart attack or stroke, didn't work. But same thing in a person with known coronary artery disease at risk for a heart attack, NTT is probably 5 or 6. So long answer to your question, but I thought some general principles might get illustrated.
Sensor-based continuous, and we have been working in the ICU space, as you know, in that direction as well. So do you think there's a need for a consortium for picking up a question which India should solve? And maybe as an outcome of this conference.
I always think there is a role of a consortium and a role of individual leadership, both at the same time. Consortium to make sure that there is diverse representation and data and everything else. And individual leadership to make sure that it's not too many cooks spoiling the soup, the broth. So there is a role for both. I have very rarely found very large meetings led to anything very productive on the main focused part. But I find after the focus part is done, a call to involve a larger number of stakeholders works well.
More questions? So I have a question about industry and its role here. So last week we were talking about LLMs, and the point was made that it is not West versus India or China. I think it is huge mega corporations controlling LLMs because they alone have the resources for that kind of computing power. Do you see some such issue here with digital twins, that to make a realistic digital twin, you need the sort of resources that government or public universities or even private universities
I think
can't?
it's a great question, also one that's incredibly hard to answer, but one that I've thought about enough number of times. So I'll tell you the little conclusions I have come to piecemeals. One is that LLMs themselves, especially with Meta releasing the public open source version of it, might also be an equalizer. While one fears that because of the tremendous amount of compute and training they took, the reality is once one of them releases it, another one to compete with them, remember the stock value of these companies is far, far greater than even those immense values we are thinking about in the academic sense. So for Facebook, approaching $1 trillion valuation at some point is more important than $1 billion of stuff given to us free. So we will see open source versions of pre-trained LLMs that might be modifiable, and the jury is still out on that one, which can have other LLMs sitting on top of them. So if you saw that Google note, which I'm sure many of you saw on the future of LLMs, it's very nicely optimistic.
Yes.
What do you, I mean, this is a question back to you. On that Google note, do you agree?
No, I mean, yeah, I do. I did read that Google note, and the guy was basically saying open source will eat Google's lunch even very soon. But the point is that, as you said, you can have a pre-trained model which actually required this mega computers to train. But once you download it, you can run it on a modest system. But to train that model, you needed Google or Facebook to do it. So there were examples of open LLMs that I gave them a spin. So I don't really know whether the note is right or wrong. But getting back to digital twins.
Now, so LLMs was the first part of the question. So I think LLMs are a solvable problem. So the digital twin part of the question actually gives India an advantage. Because in many areas, the digital twins that one would have to make in India would be so different from elsewhere that we would be a unique country with enough population, enough consumers, enough differentiated problems, that if we are able to separate the LLMs and the knowledge, and then get the two to work together, we would have an advantage. So yesterday I didn't speak much about it, but one of the things that we at Ashoka are looking at is something called Gyan AI. So it is by a friend of Ashoka, who's an entrepreneur, who started working in language models quite early and works with the larger companies. And the basic idea is separate the knowledge and separate the LLM. Don't expect the LLM to have non-hallucinatory, high-quality knowledge of the problem that you have. So LLM can have its own knowledge, but can refer to your knowledge graph. If a precise answer already exists, take the knowledge from there and then deliver it. So if we were to create our own digital twin in niche areas, take tuberculosis, for example, would be, India's ability to create a digital twin relevant to India in TB could be significantly greater. So that's where I would go with that.
Yeah.
Or nutrition.
LLM was just an example, but to go to tuberculosis, if you want to build a realistic model of lungs and pathogenesis and physiological responses and so on.
Physiology is cheap.
Okay.
Physiology is cheap. Biochemistry is expensive.
Right.
Genes are even more expensive.
So you think it's doable, basically?
Yeah.
Okay.
That's one of the reasons I push physiology a bit higher. It's cheap.
Right.
Something that gives you high quality continuous physiology data for months, years would cost maybe 25,000 rupees, even on research mode. Mayank would know the numbers better than
Any other
everybody.
questions or comments on this topic? Yeah.
Thanks for the great talk. So I guess you're talking about digitization versus digitalization, and the LLM debate came up. I think, I don't know what I would love to hear your thoughts on, previously, I think people would have assumed that to really digitalize, you need everything to be in the same format, perhaps using similar machines, and everything needs to be standardized, right? I think what these LLMs and multimodal LLMs are showing is that you don't have to be that structured. I think, different hospitals can work in different ways, use different machines, protocols. But so long as there's a digital record, it is now possible to combine across modalities, experiments. So how does that change how we think about digitalization and how
No, I think what you are saying is absolutely right, but there are more intermediary steps. So for example, one of the reasons radiology progresses faster than other areas is because of the DICOM standard, which means any machine anywhere in the world is generating data in a similar format that is easy to read. When I get to physiology, every device is outputting data in a non-interoperable format. One could, in theory, speak to the company, and each company is thinking they're sitting on a gold mine of data. So they're not very willing to, give you the tools to read that data. While in radiology, GE is not trying to make sure that only GE people can read that data. So it's all doable, but it's easier if things come in standardized, interoperable formats. Just a question of ease. It is not an impossible barrier to jump over anyway, so you're right.
There's a general question about whether you think that our understanding of physiology will ever develop far enough that we can look at the difference between the two isoforms of thalidomide, one which has bad effects, one which has good. It's a very subtle molecular difference. So would we ever be able to understand physiology?
Physiology can never take you to that level. So which is why I said physiology is that nice compromise between things that people immediately care about and what is measurable with great confidence. As you go towards biochemistry, you move towards things measurable with less confidence, for which the market is also not immediate. So physiology is just a compromise between these two. In the end, every level needs to be done. But physiology might give you success stories in the beginning. So there was a wonderful Nature Medicine paper recently on using ECGs to predict a bunch of stuff that people didn't think would be predictable. So, and this has been now validated by a completely different set, for example, at Mayo. So a lot of information remains to be found in physiological signals that are easy to acquire, which might give us the success stories that will grow this endeavor. That's about it.
Let's thank Anurag again for a wonderful talk.